This series focuses on data structures and algorithms content, and particularly in this recording I will talk the second part 2 of insertion sort algorithm subseries, coding insertion sort algorithm. I have this code to begin with, where I have a print function to display to receive an array and its size, and use a loop to display its elements one by one in a row separated by space, and at the end it will insert a new line character. In the main function I have an array that I will use for sorting purpose, and this statement will actually call this print function to display this array. First let me make sure that this code uh, doesn't have any problem, then I will proceed from there. First let me compile and link and execute. It has displayed that array on the output console. Back to the code. I want to have a function called insertion sort, and I will pass data and size into it, and I expect this function will actually sort this data into ascending order using insertion sort method. Then this will actually display the data and data afterwards. Let me create a function. Return type is void because I am not using anything that would be returned by this function. I don't want this function to return anything. I want this function to receive this data, but as a modifiable array. I cannot put constant because I want this function to be able to do sorting in place in the array itself. So I should allow this function to make changes. So avoid constant here. This insertion sort algorithm runs in different passes, right? So in the first pass, in the first pass, this algorithm will see this the data that is passed in this place here as unsorted array and sorted array. So if I only look into this data here, it will see this 18 as a sorted array, and this all these elements as unsorted array. And in the first pass what happens is it will pick this first element of unsorted array, and it will kind of and once it is picked, that means it is saved in some other variable, so I don't need to have this anymore. So it will actually create a space for and expand the size of increase the size of this unsorted array. The unsorted array size will be of 2 elements, and the so increase the size of sorted array. The size of sorted array will be of 2 elements, and the size of unsorted array will be of 6 elements, right? Now what happens is it will actually find the right position in this unsorted array for this select picked value 6 to be inserted in. So the right position will be the place which is before, which comes before 18. So you need to create a space. I mean, right position in this case we have only 2 elements, so right place for 6 will be the first place. So to create a space for 6 to be inserted, you need to move this 18 to the second place, and then after that you insert 6 here. That is what this pass 1 will do. Let us see how we can implement that. Here in first pass you need to pick this element. So I want to have a variable which will store the picked element, So let me call this pick and store the value data. This is the second element in the entire array, even if it is the first element of unsorted array, but it is the second element, so it's going to be data 1. And this is data 1. And if I want to, once I pick this value, then I can consider this two elements as a part of unsorted array. So but I need to create a space for this for 6 to be inserted. So what I can do here is maybe data 1 equals to data 0. So it will copy 18 into the second position, and you actually we also want to find we also want to let me break this into two lines, two statements, and we also want to have a variable which will actually carry the right position, correct position for this to be inserted. It could be, it is possible that this first position can be right position or second can be right position, right? For example, in this case it is first position, right position, but if we have array with this value, let's say 18, let's say 19 here, then the second position should be right position for this picked value 19, right? So we have to make sure that it functions as expected in all the possible cases. So let me have a variable to store this right or correct position for the for pick, and we want to find out correct position for the per pick in this place somewhere here. So the way of finding correct position is you want to compare. For example, if data 0 is less than pick, then the correct position will be, for example, if the first element is smaller than pick, like in this case 19, then the correct position will be this position. For example, it is equals to 1. Otherwise you want to set this to 0. By default you want to set this correct position. First, if you initialize to 0, and then if next position is found, it will set to the next position. Otherwise it will this this variable will retain the 0 value for the position, and you copy, and then finally you actually data correct position equals to the peak value. You copy the peak value into the correct position, right? So at this point I think we should get the I mean the first pass right. That means we should at least get this correct. So let us see whether it does that or not. Going back to the terminal, execution. So you can see this 6 was picked, and we have 6 was placed in the first position, and 18, right? I also want to check whether it works or not in case if the second is this second element is larger than the first element. So for that purpose, let me just temporarily insert 20 here. In this case we should have 20 should be picked and it should be inserted in the same place, but these the two elements will be part of unsorted array, and then the rest will be part of I mean these two will be part of sorted array and the rest will be part of unsorted array. Let me go and try to see the output. Now it is working. Looks like smallest is first and second. In the first pass, at least it looks to be, it seems to be working. Now let me change it back to 6. Now let's go for the second. I try to, let me try to generalize it a little bit. So if we are, this is first pass, then we can have a variable that will actually keep track of the pass. First pass I equals to 1. So in that case we can replace this by I, and we can have this I think this is a little bit different. So yeah, so let me just have this one, right? So I can have variable here and then set it. So this is a pass 1. In second pass, pass 2, let me have a print statement so that we can see the data after pass 1 and even after pass 2. Data size. In pass 2 I'm going to have I equals to 2, and the peak value will be 2, because in second pass it will be picking this value, which will be the first element of unsorted array. Now in this case this is a little bit tricky. It doesn't work that this way. Here you need to first check, let's say once it is sorted, for example in pass 2 it would be like this, 6 and 18 and 3, and you will have to check whether this is smaller than 3 or 6 is smaller than 3. For example, if we have, instead of 6 we have 1, then correct position for this 3 should be in between 1 and 18. If we have a 6, then the correct position for 3 should be in the beginning. And if we have, instead of 3 we have 30, then correct position should be on the last position, right? So we have to create a logic which actually deals with all those cases. So what you can do here is maybe you can start checking, if I equals to 2, then you can start checking from 2 minus 1. First you check this 1, and then after that you check with for 0 as well. So for that you can have a loop, in a loop you can have a j variable as iteration index for the loop, and you can start j equals to, let's say, I minus 1, and because you are going back, so j should be greater than, and you can go up to j equals to 0 index, and j minus minus. So we have this thing here, right? And here we can, what we can do is we can use j. You can compare the previous one, previous element, I mean the element which is, I mean which comes before this peak element with the peak, and if this previous element is less smaller, if it is not smaller, then it will continue ignoring. For example, in this case this is not smaller, so it will ignore. This 6 is not smaller, it will continue ignore. So but if small is found, then this peak position would be j plus 1, right? Because if a value is smaller, then you want to place this peak after that smaller value. So the correct position for this for peak value to be inserted is going to be j plus 1. And once it is found, you cannot continue beyond. For example, you can have something like this. you can have, let's say, it is already sorted, for example, 3, 6 and 9, and you have this 18 and 12. If you have this all these things sorted, for example, these elements at some pass 1 2 3 4 5, then in the unsorted array you will have, let's say, 36, 21 and 15, right? So 1 2 3 4 5 6 7 8, so it is 8 size, right? So this will be in unsorted array and this sorted array. So if you pick 36, maybe I think we should consider the previous case, this case, I mean the case where we have so in this I mean for example, it is I mean pass 1, pass 2, pass 3, and yeah, we are in 18 6 3 9 comes after that, right? So we are in this stage, right? So first in the pass 1, this 18 is unsorted array, then 6 is inserted, so and then 3 is inserted after pass 3. In the pass 4, if you select 12, then you will compare this 12 with 18, which is not, I mean 18 is not smaller, so you ignore that comparison, and then you compare with 6, and 6 is indeed smaller, then you select this 18 position, the position after 6, as a replacement position or insertion position for this picked value. So that's the reason why we have to select this j plus 1. But once you select, then you don't want to continue comparing, because you have already found out that position, so you want to exit. So for that we can use we can have exit flag. Let me have boolean type exit variable, and I want to set that exit variable equals to false first, and then want to make sure that it allows entry to the loop, and this will allow entry to the loop, and unless it is set to true, then it will loop will continue. So at this point I set exit equals to true, so it will make sure that that will be the last execution. And now here also, in each comparison, what you want to do is, you want to, once you compare with 18, then you want to move this to this position. Whenever you have an element which is larger, you continue moving to the right direction, so that you will have a right position for this 12 to be inserted. So for that purpose, we want to continue shifting this j plus 1 equals to j, and we want to then we want to skip that if let's say once this exit is set, then we don't want to shift that, because at this point if you shift, then you will be also shifting this 6 to the next position. That will cause problem. So this is the thing we have to do here, and let us see whether it works in pass 2 or not, and then from after that we will I mean refine it further. In the terminal compilation, now in the first pass it was these 2 were actually dealt. In the second pass, we have 6 right position for 3 was found, it was inserted here. Now at this point this is a sorted array, and these are unsorted array. And if I continue the same thing, same process for one thing I want to actually emphasize here is that uh, this should actually work in all combination. For example, if you, even if you have, let's say, this third element going in between, for example, instead of 3, if I have, let's say, 19, right, in the case it is 19, and it should be placed in the third position, right? So if I uh, go back to the terminal and try again, so you can see after this it was picked from the same position, it was inserted in the same position. So this is sorted array, right? And in the next case, let me switch it back to value 3, original value, and if, let's say, 6 is let's say smaller than 3, then 3 should be inserted not in the first position, it should be inserted in the second position. Let's say if it is, let's say, 2, in this case now you can see since 2 was smaller, so the position was found, is position for insertion was found to be this position, and it was 3 was inserted here. This is still in the sorted form. Okay, so now at this point we can be a little bit more sure that this is the code that is generalized enough. So we to generalize it to all the passes, what you can do is instead of having this I, we can have a loop for int I equals to, let's say, 1, because we in the first pass we started with 1, so I equals to 1, and it will go up to I less than size I plus plus. Put everything in the loop, and now this is going to be I, and correct position for pick is 0. I think this is okay, false, and we didn't need to change in this place. This is also okay. I think this should be okay. So, and actually I can remove this thing. I don't need this I anymore, and remove this part, right? So these are the variables that are used in this logic. So at this in each pass I want to display the array, print data size, right? So let me quickly check whether it works as we expected or not. So let us see this code here. In the first pass we have so I think I need to change this 2 to its original value. Let me go back and change it. It was, I think, 6. Okay, going back. So 18.6 in the first pass, these two were actually this is a sorted array, and this is unsorted array. In pass 3 we have this sorted array, this is unsorted array. After pass 4 we have this is, at this point this is clear, 12 was actually inserted in the right place. This is a sorted array, and this is unsorted array. And after that we have this is as a sorted array, 9 was inserted here, and this is unsorted array, and we have this is sorted array, unsorted array, and sorted array, unsorted array, and finally entire array is sorted, right? So it looks like it is working. So now you can see, you can take this as a complete code for insertion sort algorithm, right? And one thing is that, if you want to sort in the reverse order, for that you can just reverse this, for right, if I have this sort of smaller comparison, if I compare for bigger greaterness, we have this sorted in the descending order. And this is when we do analysis, comparison analysis of this algorithm, these two statements will actually be considered as the dominating terms. So the number of execution of this statement would be counted to determine the complexity, to see how many times these statements are actually executed. We can create a variable int count equals to 0, and we can increase because at this point, if control comes to this point, and then this if and this two if statements will be executed. So we have count plus plus, and we display that count here just before printing. Let me have pass I and count and I actually want to deal with the sorting in ascending order, so changing this to comparison for smallerness. Let me do compilation and see the output now. Now you can see the count is 1 2 2 3 1 2 4, right? But we need to consider the best case, average case, and worst case situation. So the best case situation would be if these elements are already sorted. For example, the array is let's say if I pick this the array, the sorted array from the output terminal and put it here int data size equals to comment this out. In this case, this is going to be the best case situation, right? So in the best case situation, we have the count is 1, right? And the count is 1 in all cases. What that means is this block is executed for only one time, because in the first execution this for loop actually iterates for only one time. It is exited in the first iteration. That means this block executes for only one time. That means number of times this code is executed is the number of times this external for loop executes, which actually will make the complexity linear complexity that I will talk in the next recording. If we have the worst case situation where we have this array sorted in reverse order, let's say 36, 21, 18, 15, 12, 9, 6 and 3. So if I run this code with this the array which is reverse sorted, you can see in the first pass the count is 1, in the second pass 2, 3, 4, 5, 6. That means the inner loop is executing for the maximum possible number of iterations. So here the maximum possible number of iteration for this if I equals to, let's say, 1, in that case is going to be 1, right? So it starts from 0 and it's greater than equals to 0, so 1. In the second pass it is going to be 2. So in the third pass it is 3. So this code is executed for maximum possible. That will actually make the complexity of this code, because one loop inside another loop, so it is order n square. In average case we will have a situation something like this. Some are actually sorted, some not sorted, right? So for example, if I copy this sorted form array and make some changes to it, the first two elements are sorted and I want to have one element which is not sorted here. The second, let me have this 4, so this is not sorted, and then this 4 and 12 sorted. Let me put it 9. 9 is sorted, and we have not sorted form, I mean reverse sorted form here, 9, 8, and then 8, 12, and then after that we have not reverse sorted, and then again we have sorted, let's say 16. So we have approximately 50% of the cases where we have the adjacent elements not sorted in the ascending order. In the 50% of the cases the adjacent elements are sorted in descending order. So this is the average case situation. So in this case we have the count. So you can see it is 1, 2, 1, 2, right? So you can assume that in the average case situation, this this inner loop gets executed for the half of the maximum possible, in average half of the maximum possible number of iterations. For example, if you count the total number of iteration, going back to the terminal, maximum possible iteration is when you count it, 7 plus 6, 1, 2, 3, 3, 3, 6, 6, 4, 10, 10, 5, 15, 15, 6, 21, 21, 7, 28, right? But in this case if you count it, it is 3, 4, 5, 6, 7, 8, 9, 10, right? 1, 2, 1, 3, 4, 5, 6, 7, 8, 9, 10. So it is approximately 28, 50% of 28 will be 14, so we have 10, right? So it is nearly equal to, you can consider this as a nearly equal to the half. So that half number of execution of inner loop still makes the complexity n square, or big O n square. So this is all I have to talk on this topic. In the next recording I will talk analysis of this algorithm. Thank you for watching.